Okay, what do K, B, and M represent in the model?
Spring constant, damping constant, and mass.
Spring constant. Damping constant or coefficient.
But not damping mass.
That's fine. Yeah.
I didn't get the constant.
And what's M?
Mass.
Mass.
Alright, raise your hand if you got 4.
All right, so 2 classes ago on Monday, you did a lot of group activities that involved analyzing an undamped harmonic oscillator, the harmonic oscillator that has no friction. So today we're going to talk about the introduction of friction to the harmonic oscillator. So the model for the frictionless harmonic oscillator was y double prime equals negative k over m times y, where m is the mass and k is the spring constant. Since this system is frictionless, the mass just oscillates back and forth in perpetual motion, which is why you found on Monday that the solutions were sinusoidal, right? You guessed a couple of solutions involving sine and cosine. So we're going to make this model a little more realistic today. We're going to add a term for the damping force of friction. A damping force slows the motion. It dissipates energy from the system. And our assumption is that the damping force is going to be proportional to the velocity of the mass. Is that a sensible assumption?
Sure. Can you repeat that?
The damping force is proportional to the velocity of the mass. So that is, the faster the mass is moving, the more energy is lost to friction. Does that make sense?
Yeah.
Okay. All right, so yes. Okay. So if y is position, how do I represent velocity?
dy.
dy dt or y prime. Yep. So if I'm going to make a term that's proportional to velocity, I need a constant of proportionality, which we'll call b, and I put that with a y prime for velocity. So my new equation, right, it's just my old equation, equals negative k over my, and then I also have to account for friction, and I have a y prime, that's my velocity, and I need to be proportional to velocity, and I think we write this as b over, oh, I know what I did. Okay. Start with this guy, but multiply both sides by m. It's just a little my double prime equals negative ky. Right, because mass times acceleration equals force. This is how we derived the original. I'll write that down. No, you don't have to. Mass times acceleration equals force. This is how we derived the differential equation for the undamped harmonic oscillator. We said mass. Acceleration is actually y double prime because y is position. And then force was negative k y. But then we also were going to add another force here for friction that dissipates energy from the system. So it's going to be minus by prime because it's in proportion to the speed of the object. And then when we solve for y double prime here, to get that by itself, you end up with y double prime is negative k over my minus b over my prime. And then just to make this look a little simpler, you typically let b over m be represented by p and k over m be represented by q. So we have y double prime plus py prime plus qy equals 0. All right, so I would like to convert this to a first order system. So right now this is a second order differential equation. What makes it second order?
The double prime.
The double prime. So I want to convert it to a first order system, which means I can only have first derivatives, but I can have 2 equations. So the trick here is that you just let y prime equal v, right? So y prime is velocity. This y is position, so y prime is velocity. What's velocity prime?
Acceleration.
Acceleration, which is also denoted by y double prime. So just solve for y double prime in your head, and that's what v prime is. So you end up with negative py prime minus qy. So that's our converting to a first order system. I'm not even going to bother yet. Just practicing the conversion. All right, so what I'd like to be able to do is study some solutions to this differential equation, the damped harmonic oscillator. I'm going to try to just guess some solutions, and we're going to start by choosing some values for P and for Q just to make this give us something concrete to start with. So looking at, I picked P to be 3 and Q to be 2. So I have y double prime plus 3y prime plus 2y equals 0, and I want to solve it. So I'm just going to try to be clever, and I'm going to come up with a guess for y. So I'm looking for a function y of t whose second derivative can be expressed in terms of y, y prime, and constants. Okay, so like if I solved this thing for y double prime, it would be negative 3y prime minus 2y. So I need a function whose second derivative can be expressed as the sum of a linear combination of its first derivative and itself. All right, so what kind of function do you think could do that?
A linear function. A sinusoidal.
Something with e. I need to be able to add its second derivative, its first derivative, and itself, and have them be all like terms so that I get 0, right? I need to be able to combine them all as like terms. So something with an e in it would be a guess. E to the something t, right? We'll call it e to the st. We don't know what s is right now. Sinusoidal is also a good guess, but sinusoidal was a better guess on Monday because when there was no y prime term, because you needed the second derivative and itself to be like terms, and that works when you choose sine because its first derivative is cosine, but there is no first derivative term, and then its second derivative comes back to sine. So sinusoidal worked well when there was no damping term, but now that we have this damping term, sinusoidals aren't going to work as well, so we have to use this exponential term. All right, so let's guess that there is a solution of the form e to the st, that it might exist. Let's check and see. So my differential equation is y double prime plus 3y prime plus 2y equals 0, and my guess is that y equals e to the st. All right, if y equals e to the st, what's y prime?
S
S e to the st. And what's y double prime?
2s. S squared.
S squared e to the st. All right, let's plug in y prime, and y double prime into the differential equation, see if we can come up with s's that will make this work. Okay, so y double prime is s squared e to the st plus 3y prime is 3s e to the st plus 2y 2e to the st equals 0. All right, every term on the left side of that equation has what in common?
E to s.
E to the st. Let's factor that out.
Sounds great.
So I'm left with s squared plus 3s plus 2. Yep. All right, so I've got two quantities multiplied together. The answer is 0. One or the other has to be 0, right?
E to the st can never be 0.
E to the st is never 0, right? So I just have to solve this quadratic equal to 0. Factor it, s plus 2, s plus 1, negative 2 and negative 1. So there are two values of s. So we've actually found two particular solutions. Y equals e to the negative 2t. So we found two solutions here. E to the negative 2t and y equals e to the negative t. Both solve the differential equation.
So how do we know which one's the right solution?
Well, they're both right. The question is, have we found the most general solution? Don't know yet. We're working there. We're getting there. Okay, so here's a direction field for the system. We talked about direction fields last class. Does it look like you'd expect? In a spring system that has friction, what do you expect is going to happen in the long run to the mass on the end of the spring? It's going to stop moving, right? Like it has some initial amount of energy, but then it all dissipates due to friction. So everything looks like it's kind of spiraling in towards zero. Looks a little bit curvy, like it's sinusoidal, like it starts out oscillating, but then it just peters out, lands at zero. All right. So yes, this is as expected. Okay, and then the two particular solutions we just discovered are called straight line solutions. Okay, so there is an initial condition. So you can see there are some arrows here that just go directly to the origin. Right here, here, they just head directly to the origin. There is no oscillating back and forth, right? It just there's some critical amount that you could displace it, that it just goes right back. Right? It just goes right back to rest without any oscillations. Those two, I believe, are your those are e to the negative t and e to the negative 2t. I think so.
Kaylee, you kind of shaky on this section.
I do. That's because my calc students took too long to take their tests and I didn't have time to reread the section.
Did they have some Isaacs in the group?
Do they what?
Did they have some Isaacs in the group? That's a yes.
So, does the uniqueness theorem only apply to first order differential equations and no? Like, because we got two solutions, but
Those are two solutions, but they would have two different initial conditions. Yeah. Hold on. All right, I'm going to make sure I have the answer right here. But this is, as we would expect, there is some critical value where the displacement is just the exact right amount that it just goes right back to zero, and everywhere else kind of spirals in, where it oscillates and then lands back at zero.
So does that just oscillate once?
It depends on how far away you are when you start. Yeah.
Yeah, I thought it was gonna kind of like spring back and forth and kind of approach zero. Okay, it just kind of goes to zero.
Yeah, it goes to zero. So you have to remember that this picture doesn't have time in it, right? We're looking at position on the horizontal axis and velocity on the vertical axis.
I was so challenged.
Right? Because I was using the y prime equals v prime equals system to create this phase plane.
Yeah, it's kind of like that.
Because all the lines, all the arrows work.
They kind of blend together.
All right, so now I'm going to have you start the activities that will lead you through all the details. All right, so I came up with two original solutions to the second order equation, right? So I had y of t is e to the negative 2t, and that'll be y1, right? And then y2 came out to e to the negative t, right? But this phase plane is a representation of y and v, right? Because that's why I actually did the translation where I practiced changing a second order equation to a first order system, right? Because you can only make a phase plane if you have two independent variables that both depend on time, right? So that's what this phase plane is here. I've got position on the horizontal axis and velocity on the y-axis. So this is what I'm plotting, position and velocity. Time is not really visible here. So my solutions to a system have to have two equations.
Yeah.
Okay, so if y is e to the negative 2t, what is v?
It's negative 2 e to the negative 2t.
Negative 2 e to the negative 2t, because velocity is just the derivative of position. And v2 here would be negative e to the negative t.
Yeah.
Then I'm going to use each of these to plot an initial condition, to figure out what an initial condition is. And then I can follow the direction field to sketch a solution. So let's look at y1 of 0 and v1 of 0. y1 of 0. If I plug 0 into y1, I get 1. v1 of 0, plug 0 in there and I get negative 2. All right, so that means that at time 0, I'm starting with a displacement of moving the spring 1 to the right and giving it an initial velocity of negative 2. So I push it to the left with a speed of negative 2. So I plot the point 1, negative 2, y comma v, 1, negative 2. This is the solution that I'm supposed to be sketching here. So now that I have an initial condition, now I can follow the vector field and see what happens. Curves back towards 0. And then I'm going to do y2 of 0 and v2 of 0. Maybe I'll do those in another color so we can see the difference. So if I plug 0 in there, I get 1. And then v2 of 0, I get negative 1. So 1, negative 1 is my solution here, and that looks like it's actually on the straight line.
So what's the rest of the
What's what?
What's the rest of the graph?
That's it, because we have our initial position and our initial velocity, and it just goes to 0. Everything goes to 0.
Just one thing. One, two. And that's all we have to draw?
That's all you gotta draw. Yeah.
So we should